Systems with three variables. We're going to solve systems of equations that have three variables in them. There's going to be three equations with three variables, and you'll have to solve them. We'll use elimination and substitution to solve them. You know how to do elimination and you know how to do substitution. In this case, elimination usually is a little bit easier than substitution, but sometimes substitution is a lot easier than elimination. There is a process to doing this. There is a way that I'm going to teach you how to do this, and I do not like it when people don't do it the way that I teach them how to do it, because then you make mistakes and I can't find them. So do it the way I teach you how to do it. It is the best way to do it, trust me. So to lead into systems of equations with three variables, how much does each of these boxes weigh? Figure it out. Yeah, this is something that you would easily see on an ACT test. I suppose you could guess and check that to see if it's right, but the way to do this problem is to set up a system of equations. The fact that we have this little visual representation right here of a balanced beam is telling me that this side is equal to this side. So in other words, 2 blocks of A equals 1 block of B. On this one, 1 block of C equals 3 blocks of A. And on the last one, I have 10 pounds on the right equals a block of B and a block of C. So now what I can do is I can use substitution to try to solve this equation, this system of equations. I know what B is, it's 2A. I know what C is, it's 3A. So if I use those two ideas, B here turns into 2A, plus C here turns into 3A, equals 10. And now we can solve that equation. 5A equals 10, so A equals 2. Now that I have A equals 2, I can substitute that there, and I can substitute that there. That gives me 4 equals B, and C equals 6. So that is a system of equations with three variables. There are three equations. ACT, definitely. Any of you have taken the ACT in here? Have you seen something like that on it before? Absolutely. They're always there, okay? And this is the math behind what you're doing. Now, on the ACT test, you could probably reason your way through it, but look how quickly I answered that if I set up that system of three equations and used substitution. Before we get into solving systems of three equations with three variables, we want to try to visualize what it is that we're actually finding. So with systems of two equations and two variables, the graph for each equation looks like a line. And then the lines can intersect in a single point, so they can do this. Or they can be the exact same line, so they could be that line and then the other line is right on top of it, in which case we'd have infinitely many solutions. Or they can never intersect, so that would be two parallel lines. Those are the only three situations that we can have with systems of two equations and two variables. With systems of three equations and three variables, first of all, the graph is no longer a line, it's a plane. So we're not getting lines, we're getting planes. The three planes can intersect in a single point. They can intersect in a line. They can intersect in a plane, or they can intersect not at all. Not at all is fairly obvious. They're three parallel planes. They'll never cross. The three planes intersecting in a single point is this guy right here. You got a horizontal plane and then two planes that are cutting through, and as they cut through, they make that one single intersection point right there. In that case, we have what we call an ordered triple. Rather than an ordered pair, you'll have three coordinates. I have said that several times this year. That is your ordered triple. You'll have three coordinates, x, y, z. Or A, B, C. They're written in alphabetical order. For these two cases right here, we have no solution Well, we also have no solution for this one as well, but that's kind of obvious. Even though these planes here cross, there is no one place where all three planes are touching the exact same ordered triple at the same time. So because of that, in this case, there is no solution. In this case, again, here we have two parallel planes and then a plane cutting through them. In geometry, we would call that a transversal. Again, there are no places where all three planes exist at the exact same time. So therefore, there's no solution here either. In this case, think of this as like a book. This would be the binding of the book, or a bunch of pages stapled together or whatever. This is the binding of your book, and then each one of these planes is cutting through. They're all like vertical planes, but they're all oriented so that they all cut through on this line. In this case, this is infinitely many solutions here, just like there's infinitely many solutions on this one. The solution here will be a line, and you can actually find the equation for that line. It'll have three variables, but it is an equation for a line, okay? In that case, and we'll encounter some of those in this section, but in that case, you just say infinitely many solutions. By far the easier one to work with is usually elimination. So these problems can be a nightmare. I'm telling you right now, you have this in front of you if you don't listen to what I tell you to do, and you don't do what I tell you to do in this section. There's many ways you can do it. They all are full of pit holes and traps and all kinds of other things. Don't do it any other way but the way I show you how to do it, and it will save you headaches. Do it the way I show you how to do it, and you'll probably wind up being relaxed, and you'll be sleeping better at night, and your grade will increase. So solve them in the organized manner that I show you. Okay, what I want you to do first, you have your system of equations sitting here. There are three equations. Notice that there are three variables, x, y, and z. I want you to number them right off the bat. Number 1, number 2, number 3. And if you're copying these out of your book, you want to write that system down and number them. Now what you're going to do is you're going to try to find opposites. Just like with elimination before, you want to find opposites now. So you're trying to find two ways that you can find opposites. So if I look at x, I don't really see any opposites here right now. If I look at y, I don't really see any opposites right here right now. Maybe right here I do, but not here, or not here, okay? But if I look at z, I have a positive z and a negative z here. And then I can reuse that positive z and negative z here. This looks like a really good variable to try to eliminate, okay? So what I'm going to do is I'm going to pick any two, and eliminate z. Then I'm going to pick a different combination of two more equations, and eliminate z again. That will give me two new equations without z in it. So I'm going to pick first equation 1 and equation 2. Then I'm going to rewrite equation 1. 2x minus y plus z equals 4. And I'm going to rewrite equation 2. X plus 3y minus z equals 11. And now notice that if I add these two equations together, the z's disappear. So I can do that. 2x plus x is 3x. Negative y plus 3y is positive 2y. Z plus negative z is gone, equals 15. That is a brand new equation with no z in it. And I'm going to call that equation number 4. So now I need to do this again. But I need to use two different equations. And I need to eliminate z again. So give me two equations to use to eliminate z. 1 and 3, exactly. Because that gives me opposites already. I don't have to do any extra work. So I'll write down 1 and 3. And then I'll write down equation 1, which is 2x minus y plus z equals 4. And then equation 3 is 4x plus y minus z equals 14. If you happen to eliminate two variables, all the better, because it saves you a lot of work. Okay? And that's going to happen here. So we're ready to add. We have opposites in z right here. We add these together and we get 6x. We happen to eliminate the y here. Normally that won't happen. So we're going to have to do another example where that doesn't happen so that you see what you do after this. But we eliminated y, we eliminate z, and we get equals 18. Well, look, we can solve for x right now. By the way, this would be equation 5. So I'm going to label that equation 5. Now from here, normally what you would do is you would create a new system of equations with the two equations you just made. So you'd write equation 4 and equation 5 together. And then you'd have a new system of equations. So 3x plus 2y equals 15, and then 6x equals 18. There's your new system of equations. If we still had a y sitting here, then we'd be basically back in like section 2, where we try to eliminate one variable and then solve for that remaining variable. And then we'd start back substituting to get the other two coordinates. We don't have that situation here though. We can just solve for x right now. So we're going to divide both sides by 6 and we get x equals 3. Now that I know that x equals 3, I'm going to take that and back substitute it into either 4 or 5. I can't substitute into 5 though because I don't have a y here, so I'm kind of stuck back substituting that into equation 4. Once I do that, I have 3 times 3 plus 2y equals 15. I have to go back to equation 4 or 5 because if I go back to anything else, I'll have more than just one variable remaining and that won't work. So that'll give me 9 plus 2y equals 15. Subtract 9 from both sides, 2y equals 6. Divide both sides by 2 and I get y equals 3. So now that I know that x is 3 and y is 3, I can take that information and go back to any one of my original equations over here and substitute both those values in to get z. I'm just going to choose equation 1. So 2 times x is 3 minus y, which is 3, plus z equals 4. So that's 6 minus 3 plus z equals 4. Combine like terms, 3 plus z equals 4. Subtract 3 from both sides, z equals 1. Now I have all three of my coordinates. It is an ordered triple, x, comma y, comma z. There's the answer. And then you are going to substitute in those values and check your work to make sure that you're right. In all three equations, not just one, not two, all three. Okay? This is the correct answer. And you can do this checking in your head. That's 6 minus 3 plus 1 gives me 4. That's 3. That's 9, so we got 12 minus 1 gives me 11. We got 12 plus 3 is 15, minus 1 is 14. So this does check, okay? It doesn't take long to check these. Most of the time you're going to have nice ordered pairs or nice ordered triples, nice integer values. Sometimes you'll have fractions, and that's okay. You can still check them. Now I want to point out a couple places where people are going to make their mistakes. Actually, I'll take that back. I'll wait, because there's something that we didn't do in this problem that we will do in the next problem. All right, we have a new system of equations here, and a lot of white space to use. So let's get to it. What's the first thing we should do? Number your system. So we have equation 1, equation 2, equation 3. Now what? We need to pick a variable to eliminate. Y looks pretty good. So I'm choosing to eliminate y. Now what do I do? Pick 2. That will eliminate y. Which 2 do you want to pick? 1 and 2. All right, so I write 1 and 2. And now I rewrite equation 1, x minus y plus z equals negative 1. I rewrite equation 2, x plus y plus 3z equals negative 3. We're trying to eliminate y. Do we have opposites in y right now? Yeah. So I can draw my line and add these two equations together, and I get Okay, and now what? No, that's number 4. Do that. It will help a lot, trust me. Now what? Pick 2 more equations. I already used 1 and 2, so I can't do that one again. I can go 2 and 3, or I can go 1 and 3. 2 and 3 seems to work better because I already have opposites. So I'm picking equation 2 and equation 3. Equation 2 is x plus y plus 3z equals negative 3. And equation 3 is 2x minus y plus 2z equals 0. I'm trying to eliminate y. I have opposites already, so I can just add. And I get what? Good. And now what? That is number 5. So what happens now? Yep, I take 4 and 5 and I make a new system. I rewrite 4, 2x plus 4z equals negative 4. And then equation 5 is 3x plus 5z equals negative 3. Now what? I want to try to eliminate. I'm using elimination. I want to try to eliminate a variable, either x or z. Which one? X? Okay, so I have to create opposites in x in order to eliminate x, which means I'm going to multiply the top equation and the bottom equation times something. Negative 3 for the top one gives me a negative 6 up top. 2 in the bottom gives me a positive 6, and now I'll have my opposites. So now I can draw my arrow over. And if you haven't been doing that with elimination problems, you need to do it now. Draw my arrow over, and I can rewrite that system. Negative 6x minus 12z equals positive 12. Positive 6x plus 10z equals negative 6. We have opposites, so now we can add. We get negative 2z equals positive 6, which means z equals negative 3. So now that I know what z is, I can go back to one of my 2 originals over here from equation 4 and 5, and I can substitute z in and find out what x is. So pick one of the originals, either 4 or 5. Which one do you want to use? 4? Okay. So we plug in negative 3 into equation 4, and we have 2x plus 4 times negative 3 equals negative 4. So that's 2x minus 12 equals negative 4. We add 12 to both sides, and we get 2x equals positive 8. Divide both sides by 2, and we get x equals positive 4. We're almost done. We have 2 variables. We just need the third. So I'm going to take that x equals 4. And my z equals negative 3. They're both going into one of my top original equations. Whichever one looks easiest. Maybe number 1 looks easiest. So we'll go with x. Oops, I don't want x. I want 4. Minus y plus negative 3 equals negative 1. So 4 plus negative 3 is 1 minus y equals negative 1. Subtract 1 from both sides and you get negative y equals negative 2. So therefore y must be positive 2. So my answer now is x is 4, y is 2, z is negative 3. So now I am going to point out where people usually make their mistakes on these problems, because almost always if you come to me with a question saying I can't get the right answer, I'll look in 2 different places and the mistake will almost always be there. The first place is right here. When you rewrite equation 4 and 5, and then you inevitably have to do some sort of elimination process here. Most of the time that mistake will be here, and it'll be because somebody forgot to distribute to all 3 terms, or they mixed up a negative sign as they were doing that. Okay? That mistake almost always is right there. If not, if it's not there, then most likely the mistake will be here in the second one that you did. A lot of times you'll have to do some sort of multiplying of one or both equations by a number, and that mistake will happen here as well. And I guess I should say that it also could be here in either one of these two pairs. But most of the time, when you rewrite equations 4 and 5, that's where you're going to make your mistake if you make a mistake. So if you're trying to check, that's where I would go. Okay? There's lots of little places to lose negative signs here, and I guess when I hit the erase button, I lost one there, and that's the board's fault. But anyway, lots of little places. Please follow the process that I showed you. Write your system of equations down, column 1, 2, and 3. Be very organized with labeling these equations. Trust me, it will help a lot as you try to do these. Okay? Then rewrite your system, 4 and 5, get rewritten, solve that system for one variable, go back into that system, solve for the other variable, take both of those answers back into the original system, solve for your third variable, write your system as an ordered, or your answer as an ordered triple in alphabetical order, and put a box around it and then check your answers and you're done. Okay? Very complicated, but if you follow the process, they're not that bad.